Check. Okay. So good morning, all. So I think by now you got some idea about materials, and then you also got some idea about how additive manufacturing. You know what are the different types of additive manufacturing processes. I think we have covered some of the techniques, including directed energy deposition, powder bed fusion, and then we covered material extrusion, and then similar other process. Um, so and also Professor Ravi Adimani covered some of the material aspect. Now let's I think also cover some of the materials which is like a more of advanced in terms of or how difficult when it comes to making materials which is advanced in terms of controlling the composition of the materials, right? So far I think we have actually discussed dealt about how to make simple structures or simple or like example one material. If I talk about mild steel, or if I talk about aluminum, if I talk about any other material, so where we are actually looking at more of how complex parts can be actually printed, right? So we are actually looking for more of design aspects, right? We are looking for like how easy to manufacture any complex shapes, how easy to fabricate, right? Now that we have that flexibility, right, that we can any shape that you actually see, right, any complexity, that component that you see, we will be able to actually manufacture using different or one or other way through additive manufacturing. But other side, how easy to control, right, how easy to make a component such that it should actually serve the application or serve the purpose, right? So you may have a different requirement in terms of properties, or in terms of application, right? So or in terms of like you want to have different issues in terms of material joining them together, right? So when we actually talk about a gradient structure, right, we actually go one step above composite structures. So far you might have actually heard about composite structures, right, where we actually have the different laminates, right? Of each laminate is actually made up of a different reinforcement or different matrix, right? So there we actually talk more about how to make a composite each layers, and then we actually stack them together. So here we will actually go one more step forward in terms of controlling your materials, controlling your structure, right? So if you see that how the materials as over the time, right, the history of this material, how the evolution of the material, right? So if you go back to the the materials, that how we actually started, we started the materials whatever available for us, we simply used them, right? We simply used them because it was only available for us, which is whatever the resources, starting from the stone, right? So we simply used it, and then we have used the stone for different purpose, and including cutting, and then including making different structures and so many things. And then we have actually started like categorizing the materials, based on we found that wood actually will be good for something, stone will be good for something else. But later on, we realized we want something better. We want something different, something like where space applications is actually requiring something. Like example, if you want to have a iron materials, or you want to steel materials. So you are actually started looking for something novel in terms of a material because application is actually demanding, right? We have started looking for more of a application orient. So that's where we started looking for optimizing the materials, right? If we started looking for optimizing the material, because we realized it, whatever available material may not serve the purpose, right? May not work for us. It may work for a short time, but if I see long term, or if I see that how they are actually going with the application, they are not actually doing well, right? Now we started optimizing it, the materials. Now later on, we have actually selected the materials. Now we have identified, right? We have optimized, and then we have actually started looking at like exactly this material actually will work for this, right? Exactly this material I can actually use for this application. If I look for something like a fatigue application, or if I look for something dynamic application, if I look for something static, right? And then if I want to actually construct a building, right? If I want to actually build, if you want to build the ship, that I need to have different densities, right? Now we have actually looked and then looked into more of a selected, where we saw that the lot of changes that actually happened. We slowly started looking at exactly which material will work for us, so that we can actually select for a right application, a right strategy that we can actually use it, right? So now what is it like? While doing that, we are actually looking for something more tailored material, what is today, right? So if I actually talk about say example, I have a different application with respect to the materials, or I want to actually select the different material, like where I can actually tailor the materials, which means now if you see that the trend, you will actually will see that they are actually more of a time bound, right? So they are more of you can actually give that warranty for this many days, or this many months, or this many cycles, right? You can actually set the time frame, and then you can set the time frame. You can actually choose the material, or you can actually tailor the material, or you can tailor the composition of the material, right? Sorry. So you can tailor the material now, right? So if I want to actually use the titanium, right? So if I use a pure titanium, may not work. But if I want to go for something alloys, or if I want to go for different alloys of aluminum, right? Pure aluminum may not work. But if I go for these compositions, if I actually change it, now I'm also actually setting up something like tailoring the material for my application, and also I'm also actually setting the time frame for that, right? You can actually see that many examples that you actually go to the any shopping, right, or anything you actually buy, right? Example, you also buy the battery for your car, simple example, that many times that you will actually observe after the warranty, or 1 or 2 months, you will start experiencing some different issues, right? It will not work, or sometimes it will not go well, you have to quickly replace it. So how do you actually decide such a time frame? Of course, they have different mixture of different chemicals, and then the solvents, etc., solutions, etc. But and then there is lot of things going on where you are actually tailoring your materials, tailoring your composition. You are setting up the time, right? How long, how many cycles this material will actually work, how many cycle it should work, right? So that is where we are now at the stage where you can actually select the material, right? Or you can tailor the material, you can control the material through using different compositions of the material, which is where we are actually looking at the functionally gradient structures, right? So if I actually give you the definition, right, this is a basically advanced in terms of a material whose properties can be actually tailor made, where you can actually vary the composition of the material, variation property within the material, right, within the structure, within the component, right? I can as well count it, like example, if I say this is a component, right? So can I actually change composition, one composition this side and then other composition this side, where I can actually vary entire or throughout your the component, right? I may have fully magnetic this side, I can have fully non-magnetic this side, where I don't need to join now anymore. But what I do, I actually, while making a component, I will vary the composition such a way that this side I will have completely magnetic material, this side I will have completely non-magnetic material. Now I have the leverage, I have the luxury in varying the material or changing the composition, right, through additive manufacturing, right? Why we need actual additive? So this kind of variation, or where you can if you try with the traditional manufacturing techniques, so it is a difficult or challenge that you will have when you actually mix them composition, and then you try to put them composition at different levels, etc. You'll have actually a lot of challenges. So why we actually choose this, right? Before we choose, if you actually also see that the kind of the material, which is actually how you are actually, if you look at the scales, right, you can see that microstructural, which is where we actually talk about nano levels, right, where we actually see that architectured material, where we talk about a lot of gradient structure, and then hybrid materials, where you can see that anywhere you can actually start microns to nano and meter, and then you can go for a centimeter scale and then meter scale. Now we also have the superstructure, right, where we actually talk about, as you vary your composition of the material, you can also actually control, where now we have seen a lot of control variation with respect to the microstructure by using different methods, right? Now here we can actually vary your different materials or different composition of the material, where you will be able to achieve different composition of or different structure, which is made up of a different composition, right? It is no more with just simply composite structure now, because when we actually talk about the composite structure, so think about, this is a one layer, bottom is I have the cover is the one of the material, where which is made up of one material, and then I have another layer which has another material composition, where their resolution may not be good as when it compared to that gradient structure. When we talk about the gradient structure, we actually talk about where you are varying your material composition, right, gradually or tailor made, where you can actually control your entire the composition of the material, where while doing that, we can also see a lot of multi-functionality, and then increasing importance for especially modeling, because when you wanted to see before, you can actually also do a lot of modeling before you actually see that the structure. So this is actually the heterogeneous architecture. But again, so how you are going to achieve such kind of a structure, right? How you are actually going to make such kind of a component, right? How to actually make such kind of a component is actually challenging. Now with that, we understood that what is actually the functionally gradient materials, or what is a gradient structure. As I said, the gradient structure is it is a little bit of advanced when it comes to compared to the composite structure, right? Where here we actually talk about varying the composition within the component or within the structure, where you can actually vary the mechanical properties, or you can imagine if I actually talk about simple hardness, right? So if I actually measure hardness from this end to other end, I should be able to see that a different hardness, right? But if you want to see that, but what exactly application that you are actually looking at both sides, both ends, right? Now the challenge that we have for us is, now that we understood that how actually the gradient structure should be look like, and then how to make the tailor, right? All right, we have to see the how to manufacture or how to fabricate this kind of a structure is what we have to worry, right? So as I think we have actually talked about a different additive manufacturing. Now we will see some of the challenges that you will actually find, right, when it comes to making such kind of a gradient structure. As I said, why we actually use additive for this kind of a structure, the one simple reason is you can actually control your materials. Why? Because we are only adding material how much ever it is required. We are only actually fusing how much ever it is required, right? Wherein you can actually easily control what material is supposed to go at a particular a location, or at a particular moment, or in a component. So that is basically flexibility that you have, that now you can actually control your material, where to place, how to place, right, and what material to place, right? So because you can actually transfer bit by bit, or the how much material where to, etc. So now there are different methods, or different attempts were made by using a different additive manufacturing technique for making a gradient structures, right? So we will go by one, and as a researcher you will also find a lot of interesting, because the reason being, this is a very new technology, right? Every one or other way we need such a kind of a material, where we need to actually focus on making such kind of structures, where you will actually find a lot of interesting challenges when it comes to the making of such kind of a structure, right? So you can actually go for different, like example, if I actually talk about material extrusion, which is basically FDM technology, how to achieve, where you can actually deposit two or more semi-solid polymers, or you can actually prepare the your filament with different composition of materials, or a different, like example, you can have a materials, like example, metal, different form, or you can have a variation with the different material, where you can actually make a two or more nozzles, or two or more filament will be coming together, and then making a structures. So that is one of the simple method that you will actually observe, and then it is very easy, right? I think so far you have actually seen FDM printers, how to make the filaments, how to actually feed the filament, and how to extrude it. So here you can actually use one or two or more semi-solid polymer in the form of a filament, or you can also actually supply the material through the side. I think in the previous class I actually showed how to feed the fibers when it comes to the filament, and then so that you can actually form that layer, right? So this is the one, and then we have another method, which is basically varying each laminated layers, right? So when I say each laminated layer, now your thickness of the sheets will vary, right? And it will actually, your gradient structure will depend on what is the sheet thickness. Otherwise it will be like a composite structure, right? How small you will be able to actually form the thin sheets. Smaller the better control, right? That's where we call it as a resolution, right? What is the resolution when it comes to gradient structure? The resolution is how small that you can actually have, that how small thin layer you will have the structure, so that you can actually form a gradient structure, control gradient structure. Otherwise, if you actually have a more thicker, right, which means you actually move towards composite structure, where you will have less flexibility in terms of making a gradient structure in a component, right? So you can see that a lot of laminated object manufacturing, which is the LAM, which is another additive manufacturing where, so they actually use the different laminates and then cut the profile and then get the bonding between the two layers using a different bonding method. And then we have ultrasonic consolidation, which is another technique of additive, where they use actually the sheets and then use the ultrasonic machine to weld them, which is like welding kind of a thing where you actually stack them together. Now, when they actually stack them together, you actually put the layers of a stacking, right? And then you actually make the thin or as small as possible, so that you can actually get the structure which is very thin, so that you can actually form the gradient structure. So the other one is where you can actually vary the powder layers, right? So as I said, when it comes to selective laser sintering, right? So we discussed about where you actually spread the powder, right? And then you actually selectively melt resin, and then you can actually solidify or deposit the layer. Now, so if I want to actually have a layers of different layers of material, you basically deposit one layer with one material. Since your the size of the particles or the size of the powder particle is between 80 to 100 micron, so which means you can actually control your gradient structure anywhere less than even 0.2 or 3 mm size, right? Your gradient structure, where you can actually very nicely your composition of the materials, right? So here selective laser sintering is another method, but here you need to actually have better planning in terms of varying the material, because every time once you actually spread it, the next layer, right, you have to actually have a different material, and then for that you need to have either different hoppers or different reservoir of which mixed with a different composition. Here it's a little bit of challenging when you actually compare with other the process, where you need to actually have a more amount of material, right? So this is a very easy when it comes to all other processes, which is varying the area filling paths, which is like I think we have discussed in the previous class, where we have actually talked about laser engineering net shaping, which is nothing but lens. Also, people call it is a DED process, where we actually talked about you only add how much ever material that you want. Now, if I have a more number of nozzles, where more material can be actually controlled, right? Here you can actually have one way is you can have area filling paths in this case, like and then here since as I said you can actually control. I will show in the next slide how you can actually control, and then that last and then varying deposition material, right? You can actually have different jets, like example when it comes to the 3D P, which is another jet printing technology, where you can actually have a different nozzles or jets, use it different materials to feed it, right? And then you can actually form the structure, right? And then this is another technology, which is shape deposition manufacturing, which is again here. This is actually nothing but as I said yesterday, there are n number of names for a DED. This is one of them, where you can actually mix different the powders, right? You can have a titanium, and then you can have titanium alloys, right? And then you actually mix them together, and then mixing is not a difficult, but exactly varying the composition of materials, exactly varying at a different location is what matters. Anybody can actually mix it and then put it, but exactly depositing at the right location, a right material. Like example, if I actually talk about, this is actually the component. So if I say this is a 0 0 and this is actually x say 100. At 100, right, which material should go and what composition it should, right? Because you are actually controlling through your computer. So, but you may be actually controlling, but how much it is effectively depositing that much amount of only the percentage of material, right? How I will know the titanium of 1% of a titanium and then 99% of other material is actually being deposited, so that you are actually transitioning into 100% material B. Like example, if I talk about material A this side, then material B, as I start, so 100% with material A this side, and then as I go, by the time I reach at the end of the part, so the material B will be 100%, right? How to vary and what percentage of that variation that you are actually trying? Is it 1% variation you are trying, or is it a 5%, or is it 10% variation you are trying, or is it 50%, or what is it? If you are doing it, at what interval you are actually doing it? Like example, how much time you take from moving from 5% to 10%, right? And what is happening that intermediate step? Like example, when you switch from 5 to 10%, is it intermediate is 7%, or is it 8%? Is it a step that you are actually taking? Is it stepped version is actually happening, or is it gradually changing with which is like, say example, if I change from 5 to 10, are you dividing it percentage? And then how much trigger that you are able to achieve, right? How much time you need, and what is the switchover gap? How much time you are taking, and then how much length or distance you need for switching from one composition to other composition, right? So that is where we actually deal. That's where we actually talk about how precisely or what is the resolution of your printer will decide, right? How much that switch that can actually happen, right? So there are different in terms of the materials and then different composition that you can do. As I said, making a different mixture, making a machine or doing is not an actually challenging in this case, but controlling at every location, at changing the material at every location, making sure that is actually happening is actually challenging, right? So if I see that the various gradient structure possible today, right? So you have a say example alloy A and then alloy B, right? You have a lot of step here, there is switch suddenly, right? So you can actually see that one material and then other material and then again another material, so you can see that stepped again, right? So you can also see that slowly and then another material is actually coming, right? This is another way that you can actually see. Here you can actually see that two component continuous, right, gradient. Here if you see that two components step gradient, because you are actually suddenly switching it here from material A to material B, right? Here what is happening? You are actually going two component alternative gradient, right? 1 B A B A B A B, right? So and then if you see that three components, like you can see 1 2 3, which is again this is three component continuous gradient, like you can see some gradient and then gradient and then gradient. That if you see that this is a two component, but you have the particles, right, embedded or reinforced, right? And then if you see that last one, where you'll actually find two component microstructural gradient, where your microstructures are actually helping us to make more gradient structure. So you will find one or other way this kind of a gradient structure today, right? But looking is actually very simple. If you actually look at this different possible gradient structure, looking at it's very easy. But if you when it comes to that actual making this kind of a structure, you will actually find a lot of challenging, right? So here it is possibly easy, because you actually have one parameters or one material here, and then suddenly you switch it, and then you can actually move to other material. So possibly here is very easy. But when it comes to your alternative layers, that too, you are actually switching immediately within few mms, or within say example, if I talk about 5 right? Which means I am actually deciding what is the resolution of this printer, or resolution of my technology, how small, that so that I can actually have more gradient structure, right? Better the or the smaller, you'll have better the control. That control will actually have when it comes to the powder based DED, where you can actually control your materials, right? So as I said, material exclusion, which is where we actually talked about it, some of the researchers have actually tried it out, where they have actually used different compositions. Like example, you have 50-50, and then you have 75, and then 725, right? You have 50-50 L, and then you have you have another material Jadar, and then you have the 100%, right? So you can have the different materials where you can how they are actually achieved this kind of a structure. Here you have the screw, and then you have the material A and the material B here, and then here you can actually vary, right? So this kind of a configuration you need for making a material. That's why we call it as a, you actually either use a different paste where you can actually control. Now I should know that exactly when which material should go, because you cannot actually control and then later part where you can change it. Otherwise there is a lot of time is also required from moving year to year, right? So you need to actually plan such that you actually have this kind of the structure, right? So this is actually one way. This is very common, that are easy, I would say, among other technology, where you can actually vary, or you can actually have different configurations, something like this, right? So you can actually control your the materials, so that you can actually make the gradient structure with using different nozzles. This is actually the material extrusion. So, and then you can also find something like this structures also, right, where you can again control different materials, where you can actually form gradient structure, something like this, right? So here again you need to make sure you're actually controlling those the nozzles and then the material, so that you can actually mix well, right? And then you can actually see something like gradient structure is actually being formed here, right? But question is how well what is basically the distance between this layer, right? And then how much you're actually taking time, or what is switch is actually happening for making this kind of gradient structure. So as a researcher, we have to see how to see how easy to make this kind of a structure, and how difficult, like example, how to solve when it comes to mixing of the material. Now mixing is a one, but how actually they are actually reacting, what is actually happening after making the structure, right? So there are a lot of other research that have actually tried. Like example, this is the LPB of technology, where I was actually talking about it. So you can see that when you actually mix two different material, especially when it comes to the metal, right, you will find lot of challenging, right? You can see that how much that the bad in terms of the structure here formation, right? So they don't go well because their composition is completely different. When composition is completely different, your melting is also will vary. Say example, if we talk about the melting temperature for material A may be different compared to material B, right? Now you actually try to join them and mix them together, and then you give the same power. So you may be giving power whatever it is actually required for material A, but may not be for material B, right? So there you will actually see a lot of porous, and then you will find a lot of cracks, and then you can see that a lot of pores and then cracks, because they are not actually good when it comes to the structure, or you have not actually managed well in terms of making this the structure, right? But here a lot of challenging is there, because it is not easy, especially when it comes to the powder bed fusion. Of course, they are actually trying with a different nozzle or a different because if you do something like that, typical that reservoir, and then it is like you have to mix a lot of powder and then you actually spread it, right? I mean, technically it is quite challenging for making a gradient structure in this case. That's why you have to go for something like this, mixing method, so that you can actually mix a different. Say, example, if I talk about this, you have the copper and then you have the glass, and then you try to add the something like this structure where you will actually try to make a, but not many success stories when it comes to LPBF for making a gradient structure. The reason being, you need to actually mix and then you need to actually spread the powder, and then that the spread or entire layer, you need to have one mixture or one composition, right? Sometimes you need actually a lot of powders, right? If you actually mix it, it will be difficult to separate them again, right? And then again it will be even more challenging to understand the what is exactly the composition of or percentage of this material, right? So as I said, the another technique is actually ultrasonic consolidation, where, as I said, you can have a different thin foils or different sheets, right? And then you actually use a ultrasonic machine to bind them together, right? Here, smaller the thickness of the sheet, so you will have more in terms of flexibility for making a gradient structure. Thicker, it will be difficult. Even it will be difficult to even weld them together or join them together, right? So that's why you need to see that how to make a smaller, but and also even if you go for very small or thin sheets, it will be difficult to control also, right? So you need to actually see that optimized in terms of the thickness, so that you can actually form the the layers, each layer, and then you can have different. I think there is one researcher actually tried. Yeah, so you can see that copper, and then you can see that aluminum, and then you can also see that this is initially bigger sheet thickness, right? And then eventually you had actually reduced it, right? You can see that smaller, right? And then eventually started reducing it. So this kind of a structure will give us more freedom in terms of making a gradient structure. But only the complexity here is you need to have that the composition of each material should be made up of that composition, making that but it is sometimes easily available. For example, if you talk about aluminum material or SS material, but you need to actually see how to make sure you give enough in terms of the welding or parameters, so that they can actually stick to each other, right? So here it is quite easy, because at least entire this material is actually made up of one material, which is like, it is almost like a composite structure, but they are of more very thin structures, right? Where you have more control in terms of controlling the gradient structure or making gradient structure, right? So this is and then I think the most popular when it comes to the making of a gradient structure is the DED, right? Why I tell you? Because, say example, if I want to actually control my composition, right? I only give that much amount of material, right? If I want to actually control material A, say example, there are two nozzles, right? The two hoppers are this side, or one, say example, material B is coming from this side, material A is coming from this side, right? Now, this is basically volume of the material is constant. Now, I can actually vary, say 70% of the material can come from this side, which is what the material A, and then 30% material can come from this side, and only you add up to here, or only you add up to here. Now I can actually switch to 60%, or I can switch to 50%, or I can switch to 40%. Similarly, I will change I'll increase the volume of the or flow rate of my material B, which is different, right? So there I may actually initially I may start with 100% material A here and then 0% material B, because volume of the material is constant. Volume of the material that is being deposited is constant, and then I will have that basically variation within the material A and B. Now I slowly change the material A and material B so that I can actually control my composition. What is the most important in this case is how easy to, at what stage, how quickly it will actually will switch to material B or material A, right? So if you can actually control that, right, so then your life will be easy, right? So this is actually possible. Very, I mean, you can actually easily change in this kind of the setup, because you're only adding the material how much ever it required. That is one advantage. Second advantage is you can actually control it, how much I should actually deposit, how much I should actually avoid it. Of course, at the end of the day, you may be depositing the volume of the material may be constant, but and then how easily you can actually control within the this thing, so that you can actually make a gradient structure. Again, it will also actually will depend on what is the your laser, right? That how much laser power you are giving, right? How much you are giving, so that are you giving something laser power, or only it will work for material A, or are you giving some the laser power only it will actually work for a material B. Now if I can actually control the laser power as I change my composition, as I change the percentage of my composition, now you also actually have the direct laser power formula wherein you can actually change the laser power as well, right? Now I have varied the powder composition, right? I made sure that volume of the material is actually constant, so that I don't need to actually worry about the width of the beads or the thickness of the beads, right? That I have actually taken care. Now I don't need to worry about the most important factor is that laser power, right? Say example, when you start 100% material A, right, you know that how much laser power that you need to actually give. Now you actually give that much laser power only, and then as I slowly change the composition, now you vary the laser power as well as per your composition. Now bead will actually will have beautifully deposited, because now I have actually taken care of both composition and also how much the laser power I am supposed to give, right? And then another most important, how much the shielding that I should also give. That may be minimal when it comes to this technology, because you are only using mainly the shielding purpose, but still sometime it will also actually affect what kind of a shielding material that you are using. Are you using argon gas or helium or etc.? So you need to actually see what kind of a material that you are actually being depositing, so that you can actually control it. So this is actually more of a powder based technology. And then another one is, which is basically wire arc additive manufacturing, where this is actually wire based. Here we don't actually use any laser, we actually use a plasma, or we actually MIG welding or TIG welding, where instead of one wire we actually feed two wires, right? Imagine if this is your plasma arc, and then you have the tungsten electrode here, right? And then when you have the the arc is actually coming, right, you can actually feed the wire, right, and then you can actually fuse it, right? Now you can actually change your the material, so that you can actually, I think I have one more slide. So you can actually see there are still some challenges, they are not straightforward, right? Even though I thought, like, by varying laser power accordingly, what kind of a material composition is actually you're trying, right? So but still when it comes to that right, or the intermediate between the material or the composition, you will see the lot of issue when it comes to the interface, right? You will find sometime cracks, sometime you will find that I mean, you can clearly see that the material is actually changing. The change is because of you may have actually suddenly changed. This is a too much change, right? So you are actually changing instead of 100% to 75%. That is like huge change. So there you need to actually see uniformly change. Start with like just a 5%, start with a 2%, right? Where you will not notice much, right? But here, if you actually do a sudden step, right, you will actually see huge difference, right? And then because mainly you will see that the cooling rate of material will be different, right? Solidification rate will be different, right? Some material will actually have different cooling rate, right? So there you will find a too much error. You will find cracks because of their low temperature, the solidification rates are different, right? So this is just to give you, as a researcher, we have more challenging how to address this kind of problems. Now we got the idea how to make the component. Now that is like basically when we actually start looking into in depth of the problem, so we are actually finding a lot of challenges, right? So you can actually see this kind of a structure. And then when you also actually vary, right, you will also find a lot of warpage, right? Because when you actually change the material that you've been deposited bottom layer, maybe one material, but example here you have the titanium and then you have inconel, right? So but again as you deposit the next layer inconel, so and then you have more material of inconel, but you have less when it comes to titanium, and then you will see, right? So this is basically the direct. Then you can see that some as you go slowly, right, where you actually change the compositional gradient, right, you will actually see that some betterment in this case, right, where you can actually change it because you are not suddenly changing it, right? So if you see that the stable or in terms of compositionally changing, which is like where you can actually vary less material composition. Here you can actually see most of the time suddenly you are varying the composition, wherein it will actually will end up some cracks, or you will see that later on that warpage, etc. Here you can actually see that no, nothing is actually happening because you have actually varied compositionally, right? You changed the material, but of course, again, this may be still I feel this is sudden change, but usually you should go very gradually, so then you will not find any issues when it comes to the gradient structure. So then you'll also find something like this structure when you actually go for example changing these are the microstructure where I will not go in depth of the microstructure, just to give you the idea that you will find a lot of defects when you actually try to make this kind of a component, right? But this can be, now that we are able to make the component, if you can actually eliminate this kind of defect, and then we can make a part better, and then as a researcher we should actually see how to eliminate this kind of a structure. So this is another DED made component where you can actually find here is the stepped gradient, right? You can actually see that varying steel composition here, right? So but if you actually cut it, so they are able to see that nicely varied composition. Of course, as I said, there is a here sudden changes, but if you can actually change gradually, so you will not find any sudden change in the or you will not find much difficulty or cracks, etc. And then you will find an example where people you think that this kind of applications that you need, right? You will find a lot of applications like where you need to actually eliminate multiple materials or multiple material that will be combined in single component, right? So there example turbine blades, and then you have the cladding in here, and then you can actually have the different structures here, right? And then you have the different gears, and then so many applications actually demands that where you want to actually eliminate multiple manufacturing processes or multiple joints, by using this kind of parts or deposition, right? So this is another which is basically where you have the twin wire, which is you have the two wires is actually coming here, right? And then you have the independent power sources for this, where you can control. So if you want to actually achieve gradient structure using wire arc additive manufacturing, so you will have two options. One is you can actually control with imagine you are not changing much like materials, but you are only changing the parameters. Like example, you have the weld parameters, right? Example, current, and then welding speed, and then all the welding parameter. So there, by changing the current, you will have different properties. But how you can actually change current over the within the component is one way. But if you want to see that more in terms of gradient, or more in terms of properties that you want to see, so you have to actually go for multiple materials. Like example, you need to go for material A and then material B. So this is the setup that I actually developed when I was at IIT Hyderabad. So where you can actually see that the two different wires, so it can actually come as I said, there are two ways you can make a FGM structures. One is controlling the process parameter, example current and then voltage, and then you have the controlling the properties of different filler wires, where it will actually give more wider in terms of variation in terms of the properties, right? So what we have done is we have actually varied. We have actually set what exactly the hardness value we want to achieve, right? Like example, first 3 layers we will have one set of material, right, which is material A, and then you can have another 3 layers of different sets of material, right? You can have another. You can see that the hardness value actually varied in one direction, which is the one-dimensional gradient structure, which is actually the step over, where you actually overlap each bead, right? So, and then you can also see that how closely they are matching when you actually try with the hardness, and which is basically measured versus the desired value. So again, that is one side, like where you can actually see that step. Here, instead of step, which is more challenging in this case, is like any other case, how quickly you can actually switch from parameter 1 to parameter 2, where you can actually quickly change composition of the material, which is actually, say example, here I got the hardness value of an average 226. Here I see, you see that 248. So there is sudden change. We have measured it. There is a huge variation within the interface also, but we actually took it average and then we actually plotted this link. But if you actually see in intermediate also, you will find a huge difference. But for the sake of making the structure, we just made it average so that it is easy for us for making the structure. So this is actually the x direction, where and then you have the y direction, and then so that is independently you can actually vary x and y. But here, how to actually vary x and y together instead of one direction, instead of two direction or y direction. So imagine if I actually start from here, right? As I go in this direction, I can see that variation in the hardness value. As I go in this direction, you can see that variation in the hardness, right? Now imagine if I actually prepare something like this in z direction also, right? Again, I vary that properties or composition in z direction also. That is where I can actually build a three-dimensional gradient structure, which is actually is this. Like if I actually plan it in a stacking of this 2D with varied composition in x and y in each and every layer, and then I also vary that in layer by layer, so you will be able to achieve in a three-dimensional also, right? So this is the component. Imagine this is the, if I actually cut this component, so I will actually find a varied composition across the x and y and the z direction also, wherein you can easily make a by varying different composition of the material. So let me see if I have the video. I'm not sure if so this is now the deposition is actually happening. After the deposition, so I want to make sure that layer has to be smoothened for the next layer. So or I will go for removing the material, which is I will actually go for a milling operation. Yeah, I didn't had a high speed camera so that I can capture layer wise. So yeah, this is the layer that is actually, now I'll go for a machining. So you can see that the top surface is actually cutting it here, so that I can go for a few more layers. So you can see that this is one process is done where I have actually added the material. So I have also removed the excess or sometimes you have that sparks etc. on the top of the deposition layer. So now I'll actually again go for one more layers. Like this, I can actually deposit multiple layers. Yeah, so this is the final component. I actually skipped all the intermediate the welds and then deposition. So this is the not simple component of this is actually three-dimensional the gradient structure. Okay, I think we are done. Yeah, this is the component. Yeah. So how we actually went other applications, like example, you want to actually have something like this structure where outside you'll have, especially when it comes to the preparing some of the molds, right, where you want to actually have the soft material inside and then hard material outside, and then you don't want to see sudden change in the material, otherwise you will find actually cracks, because when the molten material actually will come in contact with the surface of the material or surface of the wall inside, right, you need to actually make sure that material is slightly different from outside, or you can actually slightly vary the composition of the each inside to outside, so that you can actually vary the you can actually avoid any cracks in the molds. Like example, you can also find radially graded rod, right, something like this application where we actually try to as a demo we try to actually deposit that kind of a structure. So this is actually the where you can actually see varied composition from inside to outside, where we can actually we demonstrated as a demo. So then you can actually, if you cut it, you will actually find that variation in the composition of the properties. One this thing is, since the wire size is very big in this case, which is a point or it is like 1 mm layer, sorry, 1 mm diameter. So we will not be able to achieve higher resolution or the smaller in terms of the size. That is the limitation that we had. But I think if you want to actually make a larger component, so this will actually help us going for a more our large component where you can quickly make and another example is where you can actually also see that some of the molds that are actually required a different composition inside and outside. So this is another similar example where we actually tried making this kind of structures, right? So yeah, so these are the some of the applications. So if you see that the summary in terms of making a gradient structure, right, making a using different technologies. So if you see that most of the technologies that you will actually will find nowadays are powder metallurgy, right? I'm sure many of you actually heard of a powder metallurgy, that where they take a different compositions and then you actually mix it and then you make a green component, right? And then where you have the limitation in terms of a wall thickness, where you had to have at least of a 2 mm, and then you cannot even have a continuous structure, because you need to actually have the different composition, and then you need to make a green part something like to maintain all the composition, right? Another technique is actually centrifugal casting method, right? So there you can actually have the gradient structure, but only limitation here is you can only actually make for a cylindrical object. So something like you are actually rotating it, and then when you actually inject that molten pool inside, when you actually rotate it, and then it is easy to create thickness of a different thickness, right, of a gradient structure. But and then you can it is only limited to the cylindrical part. So if you want to actually make some complex structure, or if you want to actually make a other than cylindrical structure, it is not possible. But for cylindrical, but again you also need to actually create that the cylindrical mold for doing that activities, and then you have to make sure you're actually putting the enough molten material also, right? So that is the limitation that we have when it comes to the centrifugal casting method. So another method, I think the plasma spray forming, where I think it is suited for mostly metals and then refractory material, where you can actually vary the feed rate, and then you can actually achieve it. But only the challenge that you will have difficulty in controlling gas flow rate, and then subtract to the gun distance, which is quite challenging, especially since when you actually use a different spray. So you need to also make sure that exactly how much material, how you are actually controlling, what are the solidifications, all that, etc., is a quite the challenging. So another technique, I think, of physical vapor deposition, PVD. I think most of them uses, especially in fact for some of the physics background, I think they also use this kind of technology, where preparing the different films, right, where they can actually vary the layer thickness, or the from nano to micro. So here they will be able to actually achieve. But when it comes to the making a components, right, it is a challenging. This is easy to make a few layers, or easy to make a few thin films, but when it comes to making a large structures, so it will be like a days or months or years, right? So it is not easy to make a when it comes to the this technology. And then, as I said, as of now, I think a lot of other techniques are also actually using for making a gradient structure. But there are a lot of progress when in these four technologies, which is material extrusion, and then powder bed fusion, and laser, which is a lens or DED, and then you have a lot of wire arc this thing. But among all these things, I think more control that you will actually will find when it comes to the DED, also called a lens, because as I said, the reason where you can actually control the material composition through by controlling the how much material flow rate. And the powder that we are actually talking about, it's in micron, right? It's about like 80 to 100 micron, which is very easy to control. But whereas if you see the other process, the size itself is big. That feed, like example, if I talk about material extrusion, so the minimum size of this is 0.4 or 5 mm, that nozzle diameter, or when it comes to that wire arc additive manufacturing, where the minimum the width of the bead is not less than 1 mm, which means you have less control over the material in terms of deposition, right? But if you want to actually build a large scale gradient, yes, this technology actually proven, and especially when it comes to high deposition rate, or where you want to actually build a large the component structure, I think this technology has actually proven. But when it comes to the material extrusion, here if you want to actually make simple structures, or simple structure that you want to actually see and then deposit and then see how it is actually coming, so this technology actually is good, and then you don't need to actually require a lot of funds or money to make that structures using material extrusion. And a lot of biodegradable materials already used in this technology for making a different structure. But I think only the disadvantage, I think nowadays few researchers have actually tried metallic or desktop material extrusion technology, but however still it is limited when it comes to the making a large scale, or making mass, or batch production with this technology. So but most of the technologies that are actually exist works for polymer based feedstock. And then powder bed fusion, as I mentioned. So if you want to actually change the composition, so you need to actually change entire bed or whatever the material that you are actually feeding entirely. You have to change the composition of that the material that you are actually feeding it, where that is quite challenging. And as I said, for every time that you need to actually start, you need to actually put at least to just to start any of this powder bed fusion technology, you need to have actually a lot of material or powder material. So as I mentioned other day example, in existing our printer, just you at least you needed 10 kilos just to start the machine. But here you can actually start this machine as small as like even 100 gram. You can start with 100 gram of powder material, and then you can actually print 100 gram of the component, right? That is that efficiency that you will have when it comes to the material utilization when you compare with powder bed and then DED technologies. Here you will have better control over the material the deposition. Of course, again as I said, sometimes since you are putting the powder is actually coming through nozzle, and then based on the flow rate of your gas, right? So sometimes it can also actually fly. Sometimes it can shield well, and sometimes if you don't maintain your shield, and then you will end up with a lot of the cracks. So that is a disadvantage when it comes to the technology. But when it comes to that controlling the features is really good. That's why you can actually have better the resolution when it comes to the, when I say the resolution is nothing but how small you will be able to actually achieve, or how small the size of your gradient you will be able to achieve using the technologies actually decides that the resolution of your gradient, right? So I think again you have the WAM. I think a lot of scholars have actually tried making for making components, but again this disadvantage to this is you need to have higher like example gradient structures, then only it is actually good, right? So but if at all you want to actually make a larger component, and then there it is actually good. That's why you need to have higher layer thickness, and then and it will create a lot of rough surface. But again you have to go for machining or hybrid technique, so that you can actually make a component. So this is just a summary of how the what are the technologies that are actually available for us for making gradient structures. Okay, so I think we have another few minutes, another 5-10 minutes. If any questions, I can answer. Any questions? No?
When the metal moves from metal A to metal B,
Mhm.
there are many weak points will come.
Many?
Weak points will come. If there is one isolated metal is there,
Mm.
then if there is a notch or there where that one is there, that is the weak point.
Mhm.
But when the metal moves metal A to metal B,
Mhm.
then there are many weak points.
Weak point in the sense what?
Means their maximum stress is equal.
Okay,
That
that is
may be failure.
that is a good question. Yeah. So okay, that's why I think one of the point that I've actually highlighted. So when you actually switch from material A to material B, you should see that how small in terms of a composition, right? Say when I say how small, what is the percentage of material in which you are actually wearing is important. So if you actually vary only 2% or 3%, you may not notice much difference versus if you actually change to 50%. When you actually change 50%, definitely you will find a lot of cracks. Definitely you will find a lot of issues because you are actually changing completely. But that is actually that is the reason that why I suggest do not actually go for a step. Go for a gradient as small as possible. If you have that option of varying and then if you can actually control it, I would recommend go even 1%. Right? While doing 1%, you are also actually controlling your laser that way. Whatever your laser was supposed to perform for, say, example, material B that is actually required, accordingly, you are actually varying your laser power as well, which means you are actually trying to make the structure such that it actually suits what actually that material melting point is actually required. So that way you can actually minimize. I will not say that it will actually will eliminate, but you can actually minimize these issues, right? Again, you will find challenging, but you are actually trying to solve a big problem of joining materials, changing or eliminating multiple components. Or you think about like if by just having one side is a fully magnetic, other side is a fully insulator, which is like non-magnetic, and then think about how much you are actually trying to save. And many people have actually tried it. It is working fine. Just that you need to see that how slowly you can actually change the step, how slowly you can actually change the composition, and how much time, how much distance you need is also important. So some cases you may need a 20 or some cases you may need 100 some cases you need even 200 also to reach that level. Because as I mentioned, if you vary that 1% or 2%, you may need larger length of the component. But if you vary, say example, quickly, right, you may need a smaller length. But usually it requires a lot of attention when it comes to, because you also need to actually worry about the many other things, not just varying the composition, but you also need to worry about how concentration, stress concentration. You need to see that how solidification is actually happening, how they are actually interacting with the laser, and then after what is happening. So it is not a in a way very straightforward, like thinking about like rule of mixture. Rule of mixture will never work, right, in this case, right? But you see that huge. But as a scholar, as a researchers, we can actually see a lot of challenges in this domain, where we can actually solve, eliminate multiple components, when you actually go for a multi-material, when you go for a gradient structures. Yeah. Any other questions? I hope I have answered your question.
So then we fabricate the gradient structure, deposition of one layer, one material layer, and milling is there. After milling, the second layer is there. So why we are doing this, like indirectly?
Yeah. So we can do. There is no hard and fast rule that you should do actually milling. Why we actually do a milling? So when you actually do a with the wire arc additive manufacturing, on the surface you will find lot of uneven surfaces, because it is like a welding you have seen, right? How much ever fast, how much ever you do good weld, or how much ever you do a good deposition, you will still find lot of spotters, right? Because if you actually add another material, you still can actually cover them. It is not that you cannot cover them, but there are cases the spotters may not be fully solid, so it may be some form of a porous also when they actually fall on the surface, right? When you actually add a material on the top of already spotters, so and then you may end up some defects, right? Different porous, etc. To avoid it, you just remove like 1/3 or less than 1/3 of the material on the top, and then you can actually again add it. But you are correct, it is not actually mandatory for us to remove it. I think in fact Prashant, Veer, and then Sujata, they are not actually removing any material. They are simply adding it, making sure that they are actually controlling, so it will actually take itself, that without removing the material, they will simply will add it, and then they are trying to do the post processing, so that if there are any defect, so it will actually will take care. So that they are doing it now. It is possible. There is no hard and fast rule that you have to do it. But nowadays, many of them are actually doing without the machining. This is when I'm talking about almost 20 years back, when we started the technology, 2011, right? So we wanted to start. Those days, we didn't had a much literature, much in terms of the advancement with respect to technology. So now we have a lot of advancement, and then I think now we are in a position to do a lot of post treatments, and then many things we can do now. Yeah. Any other questions? Okay, so I think we are on time now for lunch. Let's go for lunch, and then